Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're going to start with lecture 4.2, pump performance curve. So in this chapter, you're going to learn, in this subchapter, you're going to learn on how we determine pump performance, what are the parameters that being measured, okay, and then some of the standard analysis that need to be done in order to determine the performance of a pump. Okay, before that, we start with a simple term that normally being used before we analyze the performance of a pump. So the first one is the mass flow rate, which is symbolized by m dot. Okay. And the next one is a volume flow rate, normally symbolized by Q. But the thing is, if you are into pump and turbine analysis, we normally use V dot, okay, instead of Q, and we call that as a capacity, and then the density, which is rho. Okay. Okay, next is the Bernoulli. Okay, Bernoulli equation. But in our analysis, instead of using pressure as the units of analysis, but for heat here, we use meter. So that's why the Bernoulli equation we modified into, in order for us to get in terms of meter. It is actually good for us to understand, because in terms of pressure, we don't know how does it it's much easier for you to know the performance of a pump in terms of meter. For example, let's say if you have a reservoir located 20 meters from the location of a pump located, okay, the position of a pump. So let's see if the heat, the power or heat of the pump supplied is actually 10 meters. So since the reservoir located 20 meters, but the pump power is only 10 meters, so meaning we are basically not able to supply the water or fluid from the pump towards the reservoir. Okay, so much easier for us to understand if we use meter. So that's why your equation here is being modified into P divided by rho G plus V squared divided by 2G plus Z. Okay, so this one will produce meter instead of pressure. And so next we look into the pump. Okay, this is a typical pump configuration. We have inlet P in or velocity in, and you have P out, velocity out. So inlet and outlet, there is a difference in heat here. So this is the equation. So heat equals to P divided by rho G plus V squared divided by 2G plus Z for out, minus P divided by rho G plus V squared divided by 2G plus Z for inlet. So we use energy grade line out and energy grade line inlet. So the normal saying in pump analysis is actually energy grade line. Okay. This one is actually just for the pump itself. Okay, we have an almost similar equation, but not for pumps, but the whole system. Okay, the one we're gonna discuss later. Okay, we have water horsepower. Okay, rho G QH. Okay, even though I'm before this I explained to you that we use V dot, but normally easier for us to understand, so we just use Q. But the thing is, if there's a question about capacity, so you need to know that Q is actually capacity. So here is actually V dot. So rho G Q V dot H is actually equals to rho G Q H. So you have water horsepower and then brake horsepower, T omega. Okay. So pump efficiency. So in order for us to determine pump efficiency is we need to know what is the input and what is the output. Okay, if you look here, the input will be a rotating shaft that rotates the impeller, give energy towards the fluid. So the output will be the water horsepower. So if you look here, the efficiency of a pump is rho GQH divided by T omega. Okay. So next is the some parameter which is quite important. Alright, which is this one. You have a free delivery, and you have shut-off heat, and then best efficiency point, and also the operating point. Okay, so you can read this one, but the thing is much easier for me to explain if we use a figure later. Okay, so this is a pump performance curve. Okay, you have a graph. Here you have heat. This one is heat, and this one is efficiency of the pump, and this is the brake horsepower. Okay, and then this is the heat. Okay, and before that the x-axis is Q or V dot. So shut-off heat is positioned here. What it means by shut-off heat? When V dot is equals to 0, meaning the highest heat possible supplied by the pump. How about free delivery? Free delivery is when heat equals to 0 and Q is maximum. Okay, Q is maximum. So that one is free delivery. Okay. Next we have efficiency of the pump. This is the green color here. And then you have the brake horsepower. And then the maximum of the pump efficiency, we have what we call as the BEP. Okay. So here you're gonna have H asterisk. Okay. BHP asterisk and V dot asterisk. Okay. So when you have a BEP point, which is the maximum efficiency of the pump, and then goes towards the heat, and then brake horsepower, and then the capacity, all of it is going to be symbolized by H asterisk, BHP asterisk, V dot asterisk. Okay. So typical pump performance curve for centrifugal pump with backward inclined blades. Okay. So next we talk about operating point. Okay, this one is actually the pump itself. What is the capability of the pump heat at different capacity? So you have that value of capacity, another value, so that one will produce different heat. So let's say if the capacity is here, so this is the supplied power or supplied heat of the pump. Okay, but the thing is we have another one, which is the system heat, H required or H system. This one is actually come from the problems, which is like I mentioned before in lecture 4.1. you have a reservoir, and then another reservoir here, and then you have piping connected to that reservoir, and then you have a pump position here. So when you calculate this, the heat of the system, the whole system, and then you match it with the Q, you're going to have this kind of curve. So it's actually demand, H required. When the demand meet with the pump heat, that one is actually operating point. Okay, so later I'm going to explain to you how we calculate that one. Okay, so next we proceed with this one. Okay, so it is a common practice in the pump industry to offer several choices of impeller diameter for a single pump casing. Okay. So let's say if I am a pump manufacturer, okay, pump supplier. So normally what we do is we're gonna have this same casing, same pump casing, same base with the same screw, which is to position the pump. Okay, the one is going to be standardized. Because of what? Because we want to save manufacturing costs. Okay, and then the thing is, the one that we change is actually only the diameter of the impeller. So that's why here you see you have D1. Okay, this is D1, D2, and now of course D3 and D4. So basically you have different diameter but the same casing, same base. Okay, I mean same configuration but only different diameter of impeller. So if you see here, different diameter of impeller produce different type of heat. Okay, but the thing is, why we do that? Why we put it in the same casing? Because we want to save manufacturing costs. We want to enable capacity increase by simple impeller replacement, and then to standardize installation mountings or base, and to enable reuse of equipment for different application. Okay, right, this one is going to be for comprehension question. Okay. Okay, you when become engineer later, you're gonna see this one in a catalog to select a pump. For example, your boss asking you to select a pump to supply oil from certain position or certain refinery oil tank into another place, for example. So you need to select pump. So this is typical catalog that you will see when you work later. Okay. So this is once again, okay, you have a two-stage centrifugal pump operating at 3,500 RPM. Okay. Alright. So next I'm going to discuss to you about the NPSH, which is net positive suction heat. So let's say if you have basically you have a fluid, right? Pump is actually to move fluid. So basically the fluid will, when you have a pressure less the vapor pressure, they will produce bubbles inside the fluid. Okay, imagine there is a bubbles here occurs at the same position because of the rotation of the pump, and then you have a bubbles. When the pump rotates at very high rotation, the bubble will explode. Even though that explosion is tiny, micro explosion, for example, but the thing is it is actually repetitive and occurs at the same location. So this will produce cavitation. I mean, this one will be later become damaged. Okay, need to be repaired. So become hole here. So this is the example. So in order for us to avoid that one, we need to have what we call as the term, which is net positive suction heat. What is a net positive suction heat? It's actually the difference between the pump's inlet stagnation pressure heat and the vapor pressure heat. Okay, so I think that's all for this one. So we continue later with part 2. Okay, Assalamualaikum warahmatullahi wabarakatuh.